in this module, I'm going to introduce yet another type of sets defined using closed and open sets. That is another topological property. So the definition is as follows. Definition: a set S that is closed and such that every point is a limit point of S. Every point of S is a limit point of S is said to be a perfect set. Now, I would say that this is not the perfect choice of terminology. Mathematicians, if not anything, are never known for creative naming of things. So I do not know why these are called perfect sets, but this is what we have been handed down by our ancestors. Okay, so examples. Well, closed intervals are perfect. The whole of R itself is perfect. And for non-examples, finite sets are never perfect. Except, of course, the pathological empty set. The empty set is also a finite set. Okay. Now we are going to prove that a perfect set has always got to be uncountable. This is a nice theorem that illustrates a number of things that we have been using. Theorem: any non-empty perfect set is uncountable. Let's prove this. Suppose S were countable. Then list out the elements x1, x2, x3, so on. List out these elements. Okay, be a list of elements of S. Now note that each one of these elements, x1, x2, x3, they are all going to be limit points of the set S, right? So what we do is the following. Consider some closed interval I1 such that x1 is an element of the interior of I1. It's not one of the endpoints of the closed interval I1. Somewhere inside you choose x1. So again, a picture is worth 1,000 proofs. So you have x1 and you have this interval I1. Okay. Now because x1 is not isolated, it's a limit point, we can find some y1 in this set S such that y1 is there in interior of I1 and y1 is not equal to x1 and y1 is not equal to x2. Actually, the second part is not needed. I will do it in the next step. Such that y1 is not x1. So there will be some y1 simply because this x1 is not an isolated point. I'm choosing this y1 not to be equal to x1. That's what the meaning of x1 is a limit point is. Okay. Now choose I2 such that I2 is fully contained in I1, x1 is not an element of I2, and y1 is in the interior of I2. So now we have chosen this I2 such that I2 is a subset of I1 and x1 is not an element of I2 and y1 is there in the interior of I2. Now what we do is the following. Choose a point y2 which is there in interior of I2 such that y2 is not equal to x2. Choose a point like this. Why does such a point exist? Well, such a point exists because y1 after all is an element of S. y1 is after all an element of S. I should mention y2 is also there in S, of course. S intersect interior of I2. Because y1 is there in S, it is going to be a limit point of the set S. Because it is a limit point of the set S, there are going to be infinitely many points of S which will be there in interior of I2. Because there are infinitely many points of S which are there in interior of I2, I can always pick this y2 such that y2 is not there in x2. Okay. So now zooming the previous picture, what has happened is we have this I2, and in this I2 we have our element y1. We are choosing a y2 here. Okay. Now as you can guess, we are going to choose I3. We are going to choose I3 subset of I2 such that neither y1 nor x2 are elements of I3, but y2 is there in the interior of I2. Okay. Now we are going to choose another interval I3 like this. Note, this is why I required y2 not to be equal to x2. If y2 happen to be equal to x2, I cannot do this. There is no way to do this. Okay. Now repeat this argument. That means because y2 is a limit point of the set S, there is a y3 which is there in this interval I3, and such that this y3 is not equal to x3. Okay. And then choose an interval I4 which is subset of I3, so on and so forth. So repeat this argument to get a sequence of intervals in such that xn-1 is not an element of in. Okay. But in intersect S is never empty, is never an empty set. Okay. Now S, if it were a perfect set, S would be closed. If S were a perfect set, it will be closed. Therefore, in intersect S will be closed and bounded. And therefore compact. By Hein-Borel theorem. That means by Cantor's intersection theorem, intersection of this in intersect S is not the empty set. Right? So there has to be some x in the above intersection. Right? But that's simply not possible. Why is this not possible? Well, none of the xn's can be there in this intersection because xn-1 is not going to be there in in. But this is supposed to be an exhaustion of, this list is supposed to be an exhaustion of the elements of S. This simply leads to a contradiction. This is a contradiction. This is a contradiction. Okay, hence proved. Hence proved. So this is yet another application of a variant of the nested intervals theorem to show that any perfect set has to be uncountable. Now I'm going to define one of the most fascinating objects in topology called the Cantor set. This will turn out to be an exotic example of a perfect set. It has a number of weird properties. One can in fact spend several weeks exploring all the properties of the Cantor set. Please check the reference below if you are interested in more about the Cantor set. Okay, let's check some properties of the Cantor set. Before that, I have to define it. Look at the closed interval 0, 1. Look at the closed interval 0, 1. I just call C0 to be this. Okay. Now C1, I just remove the middle 1/3. The middle 1/3. I just remove that. That is just 1/3, 2/3. Right. So I will be left with 0, 1/3 closed union closed 2/3, 1. I'm just opening the removing the middle open interval 1/3, 2/3. Now C2, what I do is the following. I remove the middle 1/3 here. The middle 1/3 here. Well, what is that going to be? Well, think about this. That's going to be an interval of size 1/9, right? So it's going to be 0, 1/9. Then 1/9 to 2/9 has been completely removed from this. Okay, 1/9 to 2/9 has been completely removed from this. So what will remain is union 2/9 to 3/9, which is just 1/3, right? Which is just 1/3, and that's going to be union 2/3 comma. Now I need to figure out what is the next one after 2/3. So that's just 2/3 plus 1/9. If you quickly do the arithmetic, this is going to be 7/9, right? So this is going to be 7/9. Okay. Now the open interval 7/9, 8/9 is removed. So this is going to be union 8/9 and 1. Okay. So I hope the procedure is clear. So you successively define C1, C2, C3, so on. And in Cn, what you do is you look at each piece of the preceding union and remove the middle 1/3 out of it. Okay. Now I'm going to leave an exercise. Give a formula. Give a formula for this. Give a formula for this. Hint. Think 1/3 per n. That's the vague hint I'm giving you. Give a formula for how Cn is going to look. Okay. Now, what are the properties of the C0, C1, C2, Cn? Well, each Ci is compact because it is closed and bounded. It's closed because it's a finite union of closed intervals. It's compact because it's bounded also. Okay. So therefore, it's closed and bounded, therefore it's compact. Look at intersection of Cn. This is going to be a non-empty closed set. Why is it going to be a non-empty set? Because by Cantor's intersection theorem, again, this is going to be a closed set, but it's also a bounded set, therefore it's compact. This is going to be a compact set. It's a closed set because it's an intersection of closed sets. So we have defined this set C, the Cantor set, as the intersection of the sets obtained by successively removing the middle 1/3 starting with the interval closed 0, 1. Okay. Now observe the following. At the first step, we removed we removed 1/3 length interval, right? the middle 1/3, the interval length is 1 by 3. At the second step, we removed two 1 by 9 length interval. Okay. Consequently, we ended up with 4 intervals. Then we removed 1/3 of that, so 4 into 1 by 27 length interval. Okay. So you see where this is going. Let's look at the sum of the lengths of intervals we have removed. It's 1 by 3 plus 2 into 1 by 9 plus 4 into 1 by 27 plus 8 into 1 by 81 plus dot dot dot. Okay. Now this is just a geometric series. The first term is 1 by 3, whereas the common ratio R is clearly 2 by 3. So A by 1 minus R, so it's 1 minus 2 by 3 in the denominator and it's equal to 1. Okay. So what this means is the lengths of intervals that we have removed from the Cantor set sum up to 1. In some sense, we have removed the whole of the interval 0, 1, at least from this naive argument. But that's not the interesting thing. The more interesting thing, I'm not saying this is not interesting, sorry about that. This is interesting, but even more interesting is the fact that theorem, the Cantor set is perfect. The Cantor set is perfect. Whoa, this is fascinating. The Cantor set is perfect, which means that it's uncountable. So even though you seem to have removed the entire length 0, 1 length interval as the sum of this series shows, the Cantor set is nevertheless uncountable because the previous theorem says perfect sets are uncountable. Okay, but before that, let's come back and think about this Cantor set in some more depth. I said the Cantor set is non-empty by using a very powerful theorem called the Cantor intersection theorem. But that's pretty stupid of me because you can show that the Cantor set is non-empty without appealing to any fascinating theorem like this. Just look at 0 and 1. Just look at 0 and 1. They are definitely going to be there in the Cantor set. Why are they definitely going to be there in the Cantor set? Because think about it for a moment. The only way by which these endpoints 0 and 1 will not be there in the Cantor set is if they are removed at some point. But at each stage, we are only removing something from in between the Cantor set, right? Not in between the Cantor set, in between the intervals that we have. So these endpoints 0, 1 will never be removed because at each stage, we are only going to remove something from the center. Nice, 0 and 1 are there in the Cantor set, but wait a second. Doesn't the same argument hold true for the point 1 by 3 and 2 by 3? Yes, it does. At each stage after C1, 1 by 3 and 2 by 3 are never going to be touched. All successive removals will be coming from within the interval. Therefore, 1 by 3 and 2 by 3 will remain unscathed and will be there in the Cantor set C as well. Okay, so will 1 by 9, 2 by 9, 7 by 9, so on, and 8 by 9. So first proof, for the proof of this, the endpoints of any Cn is an element of C. Okay, that's the first point I want to make in this proof. The endpoints are all present in the Cantor set. How does this help us prove what we want? We want to show that if X is in C, then there is a sequence Xn in C minus X such that Xn converges to X. Please recall that this is enough. This is enough to show that X is a limit point. Okay. Now, what do we do to produce this sequence xn? Well, let's go step by step. Let's look at this picture again. This point x has to be in C1, right? It has got to be in C1. It's either there in 0, 1 by 3 or it's there in 2 by 3, 1. There are only two possibilities for this. Okay. Now, if it happens to be in 0, 1 by 3, there are three possibilities. It's either 0 or it's 1 by 3 or it's somewhere in between. Those are the three possibilities. Okay. So without loss of generality, assume that x is an element of 0, 1 by 3. X is an element of 0, 1 by 3. If x is not 0, let x1 equal to 0. If x is not 1 by 3, let x equal to 1 by 3. Okay. So if it is one of the endpoints, choose the other endpoint. Okay. If x is in the middle, it really doesn't matter. The way I have written it, x1 is sort of ambiguously defined. X1 is sort of ambiguously defined if x1 is there in the middle, but it doesn't matter. Choose any one of the endpoints if x is actually somewhere in between 0, 1 by 3. Okay. So what we have done is we have produced a point x1 in closed interval 0, 1 by 3. In fact, we have produced a point x1 in C. In C such that x1 is not equal to x, right? Observe that mod x minus x1 is less than 1 by 3. In fact, to be 100% precise, I have tried less than or equal to. It can happen that it's one of the endpoints and the choice of x1 is therefore is the other endpoint. Okay, excellent. Now, how do you choose x2? Well, do the same thing. Do the same thing for 0, 1 by 3, right? What do I mean by that? Look at 0, 1 by 3. Look at 0, 1 by 3. You're removing the middle 1/3. So this is going to be 2 by 9 and sorry, this is not 2 by 9. This is 1 by 9. This is 1 by 9 and this is 2 by 9, right? X has got to be either here or here. Okay. X has got to be either here or here depending on where x is. Choose x2 to be an endpoint not equal to x. Okay. So if x was actually somewhere here, you could have chosen this 1 by 9 as the choice of x2. Okay. It is clear that mod x minus x2 is less than or equal to 1 by 9. In this way, we can produce a sequence xn in C. All are actually not, and they're actually all endpoints. Sequence xn in C such that xn is never equal to x and mod x minus xn is less than 1 by 3 power n, less than or equal to 1 by 3 power n. In short, xn's converge to x. Xn converge to x. So we have found this set xn in C such that xn is never equal to x and mod x minus xn will always be less than or equal to 1 by 3 power n, which is just saying that xn converges to x. This shows that x is a limit point. Therefore, C is perfect. So the Cantor set is a perfect set and therefore it will be uncountable as well. Note that our argument, the extents we produce are very special. They are just coming from the endpoints. Okay. But you can check once you explore and give a formula for these endpoints, which is an exercise that I have left long ago to you. Give a formula. It will be very easy to see that these endpoints, the collection of all these endpoints, is actually a countable set. Okay. So there are points in the Cantor set other than these endpoints. You might think that there are only these endpoints, but that's not true. There are points other than these endpoints. Let me just end with one more exotic property of the Cantor set. This is rather easy to see because the way it is defined itself will give this theorem. Oh, I'm hesitant to call this a theorem. Let me just call it proposition. Proposition. The Cantor set has no interior point. Has no interior point. Well, the proof of this is very easy. Proof. Suppose it had an interior point. That means some open interval AB is going to be a subset of the Cantor set. That's the only way by which the Cantor set can have an interior point. Suppose AB is contained in C. This is simply not possible. I'm not even going to write down the full proof. I'm just going to focus here. Notice that at each stage in the construction of the Cantor set, the longest interval will be, or not the longest interval, each interval will be of length 1 by 3 power n. Okay. No interval of length greater than 1 by 3 power n can be contained in Cn. Okay. So let's write that. No interval of length greater than 1 by 3 power n is a subset of Cn. So since 1 by 3 power n obviously converges to 0, 1 by 3 power n is less than b minus a for sufficiently large n. Okay. Then AB cannot be a subset of Cn. This is a contradiction. Actually, this is not a contradiction. This is a contradiction. I have assumed that I could have rewritten this proof as a direct proof by saying that no interval AB will be a subset of Cn. Therefore, no interval AB will be a subset of C. But anyway, since I have started with suppose AB is a subset of C, I will end with this is a contradiction. Hence, Cantor set C has no interior point. Okay. So this is just a brief treatment of the Cantor set. Please check the reference I have provided for a more extensive treatment. This is a course on real analysis, and you have just watched the module on the Cantor set and perfect sets.